This last video concludes the course on semantics of parallel languages. And first, I will present a few aspects of parallel programming languages in practice. So we'll get a bit closer to what exists currently as programming language, a bit less toy languages, but a bit closer to language that are used in practice. Then I will give a small presentation of what you should do during the lab session, which is the mini-C with future implementation. And I'll conclude this course on parallel aspects of languages. There are different approaches to implement languages. One is of course, in the course, we've seen classical compilation approaches where you choose a target architecture and you transform your language into an intermediate language and basically produce whatever is needed to run on a given architecture. It works very well, but it's really time consuming and you need to do a lot of optimization, and you need also to provide as many different compilers as you have target architecture for each language. So when you design a language, another approach that is sometimes more realistic is to do source-to-source compilation. So the point, for example, is to compile your language into C, and then you would rely on the set of compilers that exist for C, and you don't have to write as many compilers as there are target architectures. And C is a well-known language that can be used, that for which everybody has a compiler most of the time. So you can do this with C, or sometimes you can do it with higher level languages like Java or so on. Third approach that exists is to rely on library or domain-specific languages. In that case, you don't translate at all. You just choose a language and extend the language by just giving additional functions. But as if you want your extension to look like it's an extension of the language, sometimes it just providing functions might not be enough. You might have to inside your library reason on the program itself. So you need introspection on the language, which is sometimes possible, sometimes not. So very often the library approach is used in languages that are higher level than C. For example, in Java, you can at runtime know a bit about the status of the objects, which is very useful when you try to implement libraries that are a bit dynamic. In the next slide, I'll show you two examples of approaches to implement languages. The first approach I want to present you is corresponds to the library approach, which is proactive. So it's the two approaches I've decided to show you are approaches where there are futures because it fits with what I've shown you in the course. And in fact, it's two approaches that have active objects, that is actors and futures and objects at the same time. Proactive is a Java API with a set of tools to do parallel and distributed computing. And it's a uniform framework, and it has a formal model behind, so there's a semantics. The programming model is based on active objects. It just consists in separating the set of objects at runtime into different actors, and each actor has a single thread, so you don't have data races, they just communicate by sending messages. So you have asynchronous remote invocations that looks a bit like asynchronous function calls that we designed. And you have what is called wait by necessity, just a get on future, but it's transparent. And it comes with plenty of features and an environment for running easily the programs. The interesting aspect is that the programmer programs in a language that has more construct. It has features and it has actors, but the language is still purely the Java language, and everything is done by a library that does enough transformation of objects statically and at runtime to provide higher level features without having to extend the language itself. So basically what is given to the programmer is something that looks like function calls, or at least has a syntax of function calls because you're constrained by the language, but it they do a lot of things. Like for example, this new second new active A here. A in fact is the name of a class, so it fetches a class and instantiates a new kind of class because it's an actor made from this class. So it creates at runtime a pieces of code basically where the code and features are added at runtime to existing objects. So the approach is quite interesting, but as you can imagine, it requires quite some software engineering to be able to implement that in a natural and efficient manner. The second language I want to talk to you about is also have features on active object, and it's the Anchor language. It's a language that has objects, features, actors, and a very rich type system. So it's a full-fledged language. It's not embedded into another language. It's really a proper language, and it has a compiler, but the compiler is source to source. In fact, it produces C code that requires a specific C library. So you have a mix also of it using the library, but just inside the C part. And it's a C library that provides actors. And then the final compilation and execution is just C code. So, and the good point is that they can have higher level type systems and higher, more complex syntax or dedicated syntax. The drawback is that the syntax needs to be extended each time, and so there's a lot. The pass we do on compilation has to be done on the language itself. But the approach is quite interesting. At least they don't have to provide one compiler per target architecture. Okay, so that was for a bit for the what exists now, because those two languages I presented are languages that are still used and were designed in the last 10 or 20 years. So what I will present you now is the lab session, and the lab session consists in doing a mini C with Future. So it's an extension of the previous courses, but we won't do compilation here. We will now transform all mini C programs into C and use specific libraries. It's an approach that looks a bit like Anchor when you have a source-to-source compiler and then a specific library to support at, inside the C language the features you want to implement. Here, features. So here is the global structure and approach we want to do. First of all, we'll restrict a bit ourselves and we will just have features of integers typed as a new type int. So it will avoid us to have to reason on parametric types, and this is feature of int, of course, but we won't have more complex types. I mean, you could implement that, but that's not the basic approach, so that we will restrict ourselves to fit in to get into the real difficult stuff from the beginning and to have something that works rapidly. So functions that can be called asynchronously must all have a single parameter of that int. It's another restriction that you will have to check, but it will simplify the way you handle those functions. Same thing, it is possible to extend this to other structure, but it would require you to reason on the language itself and to do much more work on source-to-source compilation, for example. And it's not the subject here, at least not in the basic lab session. So they all take an int and return an int. For other functions, if you have them working with any number of parameters, it's perfect. But if your type checker only takes into account functions with one single parameter of any type, is sufficient. So we won't make any tests or any of anything of functions that have more than one single parameter. So even if you didn't check functions with many parameters in your type checker, it's not necessary, but it must be working for one single parameter. So first thing we would like to do, as in the course, is to extend the syntax with two constructs, get and async. Get for accessing a feature, and async for creating a feature and triggering an asynchronous function invocation. And of course, we also need to extend the type system. Fortunately, we don't have parametric type, so we just have a feature type. This is provided to you. Second step is to transform your mini-C into C. This is source-to-source transformation that takes a mini C plus future program and produce C without features but with call to a dedicated library. Third thing you want to do is a typing visitor that is able to type get and async. This is not provided, so you will have to provide a typing visitor for get and async. Of course, more details on what exactly you have to do will be given to you at the beginning of the lab, but this is the main directions. Last thing we need to have is a runtime library that uses C-thread to implement async and get. You want to have support from C to have these new features inside your program. So that's the main thing you will have to do is write in library the implementation of async of get, relying on a skeleton of library that we will provide to you. The source-to-source transformation is performed by the program minicppdlistener.p. It adds pointers, especially pointers to functions that we didn't have in minic, but you will be able to have in C, of course. It imports the right library, which is called futurelib.h, and add a cleanup phase. So this is a typical example, and your objective could be considered as being able to run this example. So the minicpp listener does that. It transforms this typical main into this target program with the main. So you can see it's for types it does nothing different, doesn't need to. For the async call, it adds dereferencing of functions. So this is pointer to function, which is a way in C to give a reference to a function. The rest is mostly the same, except that we also trigger a primitive that frees all futures before leaving. So you will have to implement that and to deal with the liberation of space, but also of threads for all futures before finishing the program. For typing futures, so you will need to modify the type checker. So if you have a type checker working, that's the best way to start. You want to extend your type checker with two new visitors, one for asynchronous function call and one for get. So the question you should ask yourself is what are the special case of async of get typing compared to what we had before? You won't have to implement exactly these rules here because you don't just have a single parameter, you have int at plenty of places. So you can, first thing you could do is just rewrite the specific version of this typing rules in the special case that is constrained by our specific case. And so if you think a bit about it, this step is quite simple and quite independent from the library. I strongly advise you to do it last because solving last minute problems with threads or solving problems with thread synchronization without having a lab assistant helping you might be very difficult. Whether writing a type checker, you've already done a couple of them, so it shouldn't be a major issue for you. So I advise you to do this last. So this is the signature of the FutureLib library. You see that we define a structure for futures themselves, which have an identifier. It can have a value stored inside, an integer result that is 1 if the future has been resolved and 0 if it's not yet resolved. So in that case, the value of value is not meaningful. And a future is generally associated to a pthread identifier. That is the identifier of the thread that is responsible for filling this future. So that's information you want to store inside the future. The other function that I declared in the .h header and that you should implement in the C library are the following. So first, there's a type definition that just says that futint is a shortcut for pointer to future int. That prevents you from writing pointers everywhere if you want to. Then one thing to implement is a fresh future, which creates a new future, so it gives it an ID and also it creates a new place in memory to put this future. So this is memory allocation uh, plus finding a new ID. This in theory, you wouldn't need it necessarily in the library, but it will be very useful for you to debug and to test your program. It's a function that just print the current status of the future. You can use it to instrument however you want your library. This is the counterpart of this. So this creates a new future and this delays the future. This is a function that will be called. So you will call it from a task when it's finished, and you will implement to fill the values when the future is resolved. So basically, what you want to have here is change the value of resolved and of value, of course. The get statement takes a future as parameter, so this will be called by the program itself, and it will wait until the future is resolved. And if it's resolved, then it returns the right value, which is the value stored here. And else, before that, it should just loop waiting until the future is resolved. So here you would have a loop. Async is what is called to create a new future and create a new asynchronous task. It takes as parameter a pointer to a function, and this function, as we restricted for the moment, should take an integer and return an integer. This thing is the parameter that is passed to the function. So this is what will be called by the programmer too. And this will be called automatically at the end of the execution of the main to free the futures, because you've created future here and you should free the memory. So this will be freed by this. So if you summarize, the code that has to be callable by the program is the function get and the function async, and the free all futures that is generated automatically, but it's also callable for the program. So this is what is called by the programmer. This is a couple of pure C aspects that you might want to know before doing the lab. So I just do a small recall of what are threads in C and briefly recall what are function pointers. To manipulate thread in C, you will just need two library calls here. Of course, there are more things in C, but you just need those two things. And this is the way you want to do it. First, you have the function pthread create that creates a thread. So this will be the ID of the thread that will create it. So this is the name of the variable that contains the ID of the thread that will be created. It's a pointer because in C, to modify variables, you give pointers. So this means a pointer to a pre-thread key. And the rest is not much useful, except that, of course, you want to know the code that will be run by the thread. So it's given by this, which is a pointer to a function that takes a void star as parameter and returns a void star as parameters. I'll be brief here, and we will probably discuss it live if necessary. Void star means pointer to anything, so it allows you to say it can be anything here, basically. Okay, so that's the function that can take anything and return anything, basically. And this is the arguments that will be given to the function. So if you want to focus on how you want to use it, this will be perhaps a bit easier to read. The line you want to write probably looks like this. So this is the error message returned by the pthread create. So you can have a look at it, and if it's the wrong value, you can raise an error. And then this is after this TID will contain the identifier of the thread you've created. This is null, we don't care about it. This is a reference to a function. The function is called runTask, and it's a function of your library that will run the task itself. And this will contain the arguments that you want to pass to one task, and that I let you decide what you want to put here. So one thing you might not know is the pointer function. So in fact, here in my example, one task is one function of my program. So I have somewhere a function that has this signature, and this so just its name is just one task. It returns a pointer and takes a pointer, and this takes a somehow a reference to this function. So this will give to the pthread create function the way to invoke this function directly. Okay, so then the thread will run, and one thing you want to do afterwards is to check whether the thread finished. And this is done by the pre-thread function of the same library. Um, Pthread join takes as parameter a thread identifier, so it waits until the end of the thread, and this will contain an argument that is passed that can contain, sorry, it will contain whatever is returned as an exit. But here you don't care about it because you will put the result in the future. So at the end, what you want to do is just, you probably want to just do pre-thread join of the right thread ID, the one that was given to you at creation, and of new. If you really don't know anything about threads or don't know anything about function pointers, without doing a long study, I still advise you to have a look at these aspects that can easily be found on the web. So to conclude, what we've seen in this course, in these two courses, in fact, are different things. We've seen different form of parallelism, some relying more on sharing memories or more on communications. We focused quite a lot on semantics for those different parallel programming models. And we've seen the link between the type system and more structured programming. We've seen different ways to implement languages beyond pure compilation solutions, also source-to-source compilers, or even libraries that can be used inside existing languages. We've studied a bit more extensively the extension of our mini-C language with futures, or I should say our mini-Y language from a theoretical point of view, and how it would be implemented for mini-C in the lab session. We've seen a bit on types and semantics, at least on how to write types and semantics, and a bit of hints on how we could prove properties. Semantics that was presented here, or type system that was presented here, is for me is not meant to be understood just as a universal solution for this kind of problems. But I hope it has given to you plenty of clues and plenty of way to write semantics or to reason on the typing or on the behavior of a program so that you can adapt it to another language if you need to. We have not seen many things more complex about parallelism. Weak memory models is the fact that it gives semantics, if you want, or properties to the fact that generally when you access memory nowadays, you don't access a central memory, but you access a cache that might not be up to date relatively to the other threads. We didn't see the rich message passing semantics. We've just seen CCS as a message passing semantics, and it's the simplest. And we haven't seen any richer type system for futures or for creating tasks and plenty of things, including things that I've done in my research, like data flow explicit futures. And that was, of course, not mentioned. It would have been a bit too far for the time we have.